Given that p of 3 is equal to 0, fully factorise this polynomial. This is what we've been leading up to. We're now using the factor theorem to help us fully factorise polynomial equations. The way you do this is basically once you know what one linear factor is, you can then use long division to factorise to factor that divisor out. So we've already done that a little bit when we learned how to do long division. But then you can actually sometimes continue to factorise when you're left with the non-linear brackets. So for example, if you're left with a quadratic, you can use the cross method to factorise, or difference of perfect squares, or completing the square, any of your factorising methods to continue to break down the non-linear brackets until you're fully factorised. Fully factorised means that it can't be factorised any further. Usually it's you'll just have brackets which only have linear terms, so they don't have any other powers on the x terms in the brackets. Or if you get to a point where one of the brackets doesn't factorise any further, which might be sometimes a quadratic doesn't factorise further if you've got like your discriminant is less than 0. In that case, it would be factorised. It would be factorised fully if you still had the quadratic left, because you can't actually factorise something with a discriminant less than 0. Let's give this a go. Given that p of 3 equals to 0, factorise this. This tells us something, and this is telling us that one of the factors based on the factor theorem. If you recall, the factor theorem tells you that if x minus 3, if you put that into the polynomial, it would be like this, and if that equals to 0, then x minus 3 is a factor. So we're kind of using it backwards now because we've been given this information and we have to revert it back to figure out what that x is. And if you don't know how to do it backwards, all you have to do is, like before we equated it to 0 to get x by itself, we're going to undo that by just equating this to x, equating that to x, and then rearranging it to get 0 by itself. So if we subtract 3 from both sides, it's x minus 3 equals to 0. This is now the factor. Okay, that's what this is telling you. And you have to be able to understand that to be able to do the next step. So what I would usually do is start the question by saying x minus 3 is a factor. That's me showing that I've understood what this part of the question is saying. Now I'll do the long division. So I'll do x minus 3 into 2x cubed minus x squared minus 12x minus 9. Now, what is x multiplied by to give 2x cubed? X has to be multiplied by 2x squared to get 2x cubed. Now I'm multiplying that onto the divisor. 2x squared times x is equal to 2x cubed. 2x squared times negative 3 is equal to minus 6x squared. Subtracting that, we end up with these cancelling, and then we have negative x squared minus 6x squared. So negative x squared plus 6x squared. That's equal to 5x squared, and I'll bring down the rest, and we can continue. What is x multiplied by to give 5x squared? X has to be multiplied by 5x. Multiplying the 5x onto my divisor, I have 5x times x is equal to 5x squared. 5x times negative 3 is equal to minus 15x. Subtracting that away, these cancel off. Awesome. Then we have minus 12x plus 15x, which is equal to 3x minus 9. That's the minus 9. Last step. What is 3 multiplied by to give 3x? That's just 3. Then we multiply the 3 onto our divisor. 3 times x is equal to 3x. 3 times negative 3 is equal to minus 9. When you subtract that away, you get a 0. That's a fantastic thing. We are looking for this 0 because we know that the remainder should be 0. We've been told that this is a factor. If you get to this point and the remainder isn't 0, you've probably made a mistake because you can't continue to factorize unless this is 0. The reason that we can actually continue to factorize is, if you recall, our polynomial can be rewritten as the divisor times the quotient plus the remainder. In this case, the remainder is 0. So we can cross that off and just write the polynomial p of x as just the divisor multiplied by the quotient. So let's go ahead and do that. If we write the divisor, that's x minus 3. And we put the quotient, we've just found the quotient here. That's 2x squared plus 5x plus 3. And we would normally write the remainder, but the remainder is 0, so we don't have to write that at all. This is now what I was saying before, is that we've actually been able to factorize out the first factor that we were given in the question, which was x minus 3. Now, to fully factorize, because we were asked to fully factorize, we should continue to see if we can factorize this nonlinear term and see if it continues to break down in any way. A good thing to do first is, if you can't immediately see how it's going to factorize, just quickly do the discriminant check to see if it is an actual factor that can be broken down. So if we substitute, remember for the discriminant, this is b, this is a, and this is c. So if we substitute that in, that's 5 squared minus 4 times 2 times 3, which is 25 minus 4 times 2 is 8, times 3 is 24. That's equal to 1. That's larger than 0, so it can be factorized. There's definitely going to be some way that we can factorize this expression. So let's try to see if we can factorize that down. We can use the cross method in this one. So let's draw our cross out, and we'll think about two things that give 2x, so maybe 2x and x, and then two things that give 3. Maybe we can do 3 up here and 1 down here. And if we try to multiply across the cross, that's 2x plus 3x. That does give us 5x. And so our brackets will be this and this. This is where, in this topic, we start really coming back to a lot of the pre-existing knowledge that you should have, like factorizing quadratics, because you're going to be doing factorizing quadratics within your steps of factorizing bigger polynomials. Okay, so my brackets are going to be 2x plus 3 and x plus 1. Okay, so now this is a fully factorized polynomial. It's fully factorized because each x that you can see only has a power of 1. So all of these are linear factors, and therefore this is a fully factorized polynomial. And if you wanted to verify that this is correct, so I'm not going to fully do this, but if you wanted to check, you can expand the thing that we just found, which is the factorized form. And I would encourage you to do this if you had time on a test. If you expand this all fully out, then after a bit of work, you should end up with the original expression, which was given to us in the question. And if you get that, you can be confident that you have correctly fully factorized this polynomial p.